All right, so we got cut off for a minute. Here's video number 2. But we left off by saying that we can notice that as t increased from -2 to -1, I was moving this way. It's a little harder to say that you're moving left to right here because the orientation of the actual shape, right, it's like a sideways parabola here, is changing. So maybe something like saying clockwise would be a little bit better, but it's not a full circle. So you want to mark. You can never shift your arrowheads, okay? So once I've determined the direction, I want to imagine that I'm starting here and traveling towards there. I can never turn around and go back. So my arrowheads should be consistent, and here I was moving that way, and I'm going to continue moving that way. 2 arrowheads is probably enough. Don't do too many so you don't make any errors. I did want to show you guys how to do this on your graphing calculators. So if you have one in front of you, either in class or at home, there is a way to graph these to check your work on the grapher. You want to go ahead and change your mode. So mode is right next to second. So I'm pressing mode here. And if you go down, we're typically operating in the function territory here. That would be like your regular XY plane. So we want to move over to PAR for parameter, and then press enter so that parametric mode is highlighted. Then you can quit out of that screen. Now, when you press Y equals, something totally different is happening here. Like I have an old one saved. If you notice, right, the little dash here, it's every other line that it's occurring. And that's because in parametric mode, it is waiting for you to type in your X function and your Y function separately so that you can define one single parametric set of equations. The other thing that's noticeable, when you press your X button right underneath mode, right, typically we press that to pull up an X. Now when I press that same button, it pulls up a T. So that is my, my third variable that I'm defining. So we could go ahead and check our work. So for example, I could type in maybe example 1. T minus 1 was my X. 3t plus 1 was defining for my Y. The other thing you have to pay attention to here is your window. So you might need to adjust your window, press window for you. And I would suggest when you're working with just a regular equation, not trig, you probably want to make your min -10 and your max +10. So this is like saying, well, I'm going to plug in all these values, right? So perhaps on example 2 here or example B, you would only plug in a min of -2 and a max of 3. And then the other thing that you have to tell it is your T step. If you go too big, so for example, if I put 1, they're only going to plot -10, -9. They're going to count by ones. Think of your step as count bys. And they will connect the dots. So if you have anything that has a curve to it, this can sometimes make it look a little bit choppy. So you want to choose a small enough T-step, maybe 0.1, so that you get a really nice curve. You're connecting a lot of dots so that you can see that curve, rather than maybe only counting by a full 1 unit. Don't go too small or your calculator will get stuck thinking forever because it'll be plotting so many points between your min and your max. And then your regular window is just your normal piece. So like if your function was moved over, right, you would understand hopefully how to move your X's and your Y's. So I can leave those alone for this particular example. Now when I hit graph, it will look exactly like the XY plane, but if I were to hit trace, right, it's going to give me these values that are associated with my T values and my X and Y values. So that one, hopefully, right, we could check that against the front side, is a perfect copy of my, my graph. So we could try it again. We could work on the second one. And I could type in, what was it, T squared minus 4, and type in T divided by 2. Whoops, divided by 2. The other thing that's interesting, you can also view your table. So second graph pulls up your table, and you could sort of check your work. You could adjust your count bys in the table settings, or you could test your particular values that way. So this is a really nice way to see your graph. Right. This one I didn't adjust, right? This doesn't match my original, and that's because I left it at -10 to 10, whereas that particular problem only asked me to graph for t's between -2 and 3. So now when I press it, it should be a perfect match with what I sketched out before. You won't be able to use your graphing calculators necessarily on the chapter test, but when you move into BC Calculus, you'll do calculus with parametric equations, and it's important for you to see them on here and to know. The other good thing is you can check your work. So if you're stuck on something and you can't figure out what it looks like, you could use your calculator hopefully to help you get through that. The other way to work through graphing is on the next page. So we can talk about limiting the parameter. Essentially, you're switching back and forth between the parametric system and the rectangular. It's really simple to do. It basically involves substitution. So if I have a pair of parametric equations, but I want to rewrite it as a single rectangular equation, I can do that with simple substitution. If x is equal to 7t plus 3, then I could solve that for t. Right? Imagine you're in Algebra 1, right? You would talk about subtracting 3 to the other side, divide by 7, and I can rewrite that relationship. Then I could take that and I could pop it into my y relation. And I could go ahead and simplify. So when I simplified, I got negative 6x over 7 plus 18 over 7 plus 8. And I'm running out of space here. I ended up with y equals negative 6/7 x plus 74/7. Rather than picking a bunch of points, my t values, I could just convert it over to rectangular, and then I could go ahead and graph it in rectangular form. Right? 74/7, that's a little bit bigger than 10. So I ended up graphing it right here and labeling it. So my scale is probably not perfect, but at t equals 0, and then I picked another point at 74/6. I solved for my 0 on this end, and I was able to sketch my linear function. So I used my x and my y intercepts. The only thing that this doesn't get for you that the table does is that you miss out on that directional nature. So in order to get your orientation, to figure out the relationship with your t values, just pick two values. When t is 0, right, I would be getting 3 and 8. So roughly, right about here. This is my t equals 0. I need to figure out when t is 1, am I going this way or am I going this way? So I plug it in and I get a value. When you plug in 1, you end up getting 10,2. Right? 7 plus 3 is 10. I'm plugging it into here. So I'm kind of mixing my methods, right? And 10 is going to be further over, right? So it should be in this direction. So t is 1 is roughly over here. And that would mean that as t increases, I am moving from left to right. And so I would want to add my directional arrows in that way. Still regular arrowheads to say that this line goes on forever, but the directions tell me the association with the t. As t increases, I'm falling down the line. Limiting the parameter can get you in trouble, so you need to be a little bit careful. You've got to think about your domains and your ranges for x and t, and we'll come back to that in a few minutes with one of the later examples. Here, right, I won't have any issues because the domain and range of this are all real numbers. They're both linear functions, so there are no t's that I can't select. There are no y's that I won't be able to come up with or x's that I won't be able to come with. But we'll come back to that in a few minutes. I'm going to switch videos now because I think I'm running out of time, and I'll be right back.